beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. They've already wiped out the dinosaurs and many other species. And there's no doubt they will strike again.
It would be a disaster far beyond biblical proportions.
Investigating asteroids isn't just about science.
Asteroids are going to be one of our biggest problems for humanity.
It's about survival.
So the smarter we can get before then, the more we can figure out, can we do anything about it?
Get ready for the latest asteroid discoveries and daring new plans to go where no man has gone before. It's the year 2029, and an asteroid that scientists have been tracking for decades is passing close to Earth. The asteroid is about 3 football fields wide. Its name is Apophis, after the ancient Egyptian god of destruction. According to the latest predictions, Apophis won't hit Earth in 2029. But as it passes through a seemingly nondescript area of space nearby, the world's scientific community goes on high alert.
Astronomers have calculated a very small region of space, which if Apophis happens to go through that region, then it will be set up for a collision with Earth in 2036. And this very, very tiny region, which is less than a mile across, just a few thousand feet across, is called the keyhole.
An international cooperative of space agencies launches a rocket to take on Apophis.
Now, you don't want to blow it up with a nuclear weapon. First, that would take a lot of energy, and it would just produce a huge number of fragments all heading toward the Earth. What you really want to do is give it a bit of a push that slightly changes its trajectory. That way we don't get a collision.
But it's possible that the 30-million-ton space rock could simply be too massive. The collision hasn't knocked the asteroid far enough off course. The impact in 2036 is thousands of times stronger than the atomic bomb dropped on Hiroshima. The immediate crater is as wide as the island of Manhattan.
It would create a crater over 2 miles wide. If Apophis were to hit a city, goodbye to that city and the surrounding region for 100 miles.
From the shockwave, the blast, the winds coming out, from the impact ejecta, and from the massive earthquake equivalent that would occur, that would reach out and be felt over huge areas.
When Apophis was first discovered in 2004, the initial odds of an impact were about 1 in 37. But those odds have been dropping over the years, as scientists have obtained a better look at its path.
You can make the analogy that the orbit determination process is similar to predicting hurricanes. When a hurricane first starts out, you don't know exactly where it's going to go. And as you get more and more data in the next week or two, you can refine your predictions. And so it's very much like that with asteroids and comets. The more observations you get over time, the better you know where the object will be in the future.
That's why today's odds of an Earth impact, only 1 in 250,000, are so much slimmer than the original 1 in 37 prediction. But even if Apophis doesn't hit Earth, there's no doubt that something else eventually will. It's a disaster that space agencies take very seriously. In July 2010, a NASA advisory panel recommended the creation of a planetary defense office to figure out how to detect and deflect any asteroids heading our way.
We know for a fact that an asteroid is going to impact the Earth sometime in the next 1 to 10,000 years, a big one. And it's a good question as to when it's going to happen and are we going to be ready for it when it does.
A seaside amusement park is an unlikely place to demonstrate how asteroids and comets speed around our corner of the universe. But an arcade attraction here actually reveals a lot about these deadly objects.
Our solar system is kind of like a shooting gallery. Asteroids and comets can occasionally hit planets and moons, creating gigantic impact craters. Now, the bigger objects present a larger cross-sectional area, so they're easier to hit. In this case, I actually have to hit these little bullseyes, which are all about the same size. But imagine that the man over there is Jupiter. He's big, and the chipmunk might be the Earth, smaller, and these ants might be our moon, even smaller. So Jupiter is pretty easy to hit. Earth, the chipmunk, is harder to hit. It's a smaller cross-sectional area. Ah, there it goes. Earth was hit. The ants are small, so they're even harder to hit. Most of the asteroids miss. Only occasionally do they hit.
But unlike the shooting gallery, where the bullets, or in this case flashes of light, always travel in straight lines, asteroids and comets curve toward their targets.
Jupiter tends to draw in the asteroids and comets through its gravity. So it's kind of like if I start with my aim way over there, Jupiter pulls the barrel of the rifle toward it, giving me a direct hit.
Since Earth is much less massive than Jupiter, its lower gravity doesn't draw in as many asteroids. And the Moon, with only a fraction of Earth's gravity, attracts even fewer. But as the Moon's crater-pocked surface illustrates, infrequent asteroid impacts over a long period of time still means plenty of destruction. Jupiter's ability to pull in comets and asteroids has been on display a lot recently. In 1994, the Shoemaker-Levy 9 comet fragments pounded Jupiter. Scientists thought this kind of large impact was a rare event, something to be seen once every few hundred years. But then another comet or asteroid hit in July 2009. It created a large dark spot and a fireball as large as the Earth.
Seeing two different sets of impactors hitting Jupiter only 15 years apart gives some indication that the solar system might even be busier than we thought.
Then, in June 2010, a third object hit Jupiter, with an amateur astronomer capturing the moment of impact. Would this force scientists to change their estimates and acknowledge that Jupiter is hit by large objects much more often than every few hundred years?
I think that there's not necessarily many more than we thought before. And that's because the object that hit in 2009 was smaller than Comet Shoemaker-Levy 9. And there are many, many more small objects flying around there than there are large objects.
But information about any type of impact, large or small, is always helpful.
To understand the impact hazard on Earth, we need to understand the asteroid population, their orbits. So every piece of information, even if it's understanding how often they hit Jupiter or are out in the Jupiter region, contributes to our understanding of the overall population of objects in the solar system and how concerned we need to be about Earth impact.
The major source of that population is the main asteroid belt between Mars and Jupiter. That's where the strong gravitational pull of Jupiter has kept millions of smaller rocks from becoming another planet. But that's not the whole story.
So we think of asteroids as those things that just live in the belt between Mars and Jupiter because that's historically where most of them were found at first. But in fact, there are asteroids that travel way out past Jupiter. There are asteroids that come close to the Sun, asteroids that come close to Earth.
The largest asteroid is 600-mile-wide Ceres, which would stretch from Washington, D.C. to Chicago. It's so large that it makes up about a third of the total mass in the asteroid belt. An impact from something like that would be very bad news for every living creature on Earth.
It's about 100 times bigger than the impactor that caused the Chicxulub impact, which resulted in the extinction of 70% of the species on Earth and dinosaurs. So right off the bat, it seems like a bad thing, but it's a really, really bad thing. It would be a disaster far beyond biblical proportions. It would create a crater nearly as big as the United States, but while it was doing that, it would spew out molten material around the globe, create supersonic winds around the globe. It would be ugly.
Luckily, Ceres is in a stable orbit around the Sun, and large asteroids are easy to spot and track. We'd probably have decades of warning if an asteroid larger than a mile wide had a chance of hitting Earth. But the smaller ones present a tougher challenge, as the latest information shows.
There's far more small ones than large ones. So if you say the objects that are 1 kilometer or 2/3 of a mile in diameter or larger, we think there's about 940 of those, and we've discovered 86% of the population. If you move to smaller objects, say 100 meters and larger, we think there's about 50,000 of those, and we've discovered 10%. And if you move to smaller still objects, 30 meter and larger sized objects, we think there's about 2 million of those objects, and we've discovered much less than 1%.
Better telescopes coming online over the next decade will allow astronomers to identify many more asteroids of all sizes. But a 30-meter or 100-foot wide asteroid on a collision course with Earth might not be discovered until just before it hits. And something that size could still pack a devastating punch. Earth is covered with evidence of past collisions with asteroids. And today's scientists are working feverishly to figure out what's coming next. They know that enormous space rocks have wiped out most life on the planet in the past.
The good news is that they don't hit very often. It's measured in many millions or tens of millions of years, and they're big enough that through our observations, we know where those objects are, so it have long lead time and warning. It's actually the smaller ones that are the bigger risk because they happen more often and they're harder to find.
Imagine that one of these smaller asteroids is streaking toward a city. It may not be spotted until just a few hours before impact, leaving little time for evacuation and no chance to try and deflect it in space. If it's about 100 feet wide on impact, then it will hit with the energy of a 5-megaton nuclear blast, 400 times more powerful than the atomic bomb dropped on Hiroshima.
When it hits the Earth, it can cause a lot of damage because the crater that's produced is typically 10 or 20 times the width of the incoming object. So that would be 1,000 or a few thousand feet. And many miles surrounding the impact region are affected by all the debris that gets ejected. You'd have all this stuff raining down upon you.
But even if the asteroid hit hundreds of miles from the city, it could still create chaos for the millions of people living there. The food supply for the city residents could be drastically altered. if the asteroid hit a major agricultural area nearby.
Not only would all of the humans there be very likely dead, but it would sear hundreds of square miles of the growing lands. It would destroy all the current crops, and it would render the area pretty unusable for quite a period of time.
And smaller asteroids don't even need to impact the ground to cause widespread destruction. In 1908, an airburst from an asteroid that broke apart in the atmosphere leveled an estimated 80 million trees over hundreds of square miles near the Tunguska River in Siberia.
When an asteroid or a comet is coming toward the Earth, it first encounters the atmosphere, and it squeezes it, it compresses it, and that pressure causes the asteroid or comet to explode. That explosion then spreads the energy over a vast region of the ground below it. So these atmospheric airbursts are very dangerous as well.
But the rock that caused all of that destruction may have been even smaller than first thought. When it hit the atmosphere, the Tunguska object may have been only a few dozens of yards across, instead of hundreds of yards, as originally estimated.
At first, it may seem like a good thing, Tunguska smaller than we thought, but it's actually a bad thing for our future predictions, because there are more smaller objects than larger ones. So if a small object can cause that much damage, then that means it's going to happen more often than if it were a big object. We may have that impactor every few hundred years instead of every few thousand years.
At the really small end of the scale, below about 100 feet, space rocks are often known as meteoroids instead of asteroids. Shooting stars are caused by meteoroids burning up in the atmosphere. They're sometimes captured by amateur cameras, with some small chunks hitting the ground or even cars or buildings. In fact, the Earth's atmosphere is pelted with objects from outer space far more often than most people realize.
I'm here at this active rock quarry next to this big pile of crushed rock because this is about the amount of stuff, the amount of dust and sand and pebbles that hit the Earth's atmosphere every day, about 100 tons. That's enough to fill about 6 or 7 of these dump trucks. Now down here, we've got a basketball-sized rock. On average, about 2 of these slam into the Earth's atmosphere every single day. Next is the small car-sized object. Imagine this pile of rocks as one object slamming into the Earth's atmosphere, about the size of a small car. This happens about once every 2 weeks, but even something this big is probably going to burn up completely before reaching the Earth's surface. For a typical object hitting the Earth's atmosphere, it needs to be at least 100 feet in diameter to actually do serious damage to the surface. Now, 100 feet is a really big rock. That's like going from the front of the dump truck over there all the way to that orange cone over there.
At the other end of the spectrum is Earth's largest confirmed impact crater. Located in Vredefort, South Africa, it stretches more than 180 miles across and drastically changed the ancient Earth when it hit about 2 billion years ago.
It would have sent a sheet of material into space, which would then have come back and impacted on the Earth, ignited fires if there was anything to burn. And the climactic effects from that impact would have lasted for decades. The oceans would have been completely acidified. There would have been tons and tons of soot up in the atmosphere. And so that is something that we really would not want to see happen.
For the primitive life on Earth at the time, it was a major extinction event, with a crater more than 1.5 times larger than the one that wiped out the dinosaurs. The South African crater wasn't discovered until the 1990s. since most of its features had eroded in the last 2 billion years. But photos from space revealed its existence. A hilly region in the center of the deep crater initially had scientists thinking that there'd been volcanic activity in the area. But it's actually what's known as a central rebound peak, a distinctive feature for craters about 100 miles wide or larger.
As you get to larger sizes, the energy of the impactor is so high that when it comes in, the rock essentially acts like it has no strength. Then what you get is something very much like when you drop a pebble in water and you see that rebound peak as the water fills in, comes back up. But since it is rock, it then solidifies. And we see lots of these central peaks on the moon and elsewhere in the solar system.
But there are other large asteroids that have hit much more recently. Even more recently than the dinosaur-killing asteroid from 65 million years ago. 30 million years later, another massive asteroid pummeled the east coast of America and helped form what is now Chesapeake Bay.
We see evidence of debris from that impact all the way up and down the eastern seaboard, all the way up to New Jersey, New York, and comparable on the south end of it.
The 55-mile-wide crater was hidden from view underwater until oil exploration confirmed its existence in the 1990s. And since the asteroid hit just offshore, it created a massive tsunami.
Some say that the waves could have been 10, 20, maybe even 30 miles high. That's a big wave. The Appalachian Mountains are only a few thousand feet high, so even though a lot of the wave was diminished as it went inland, that's a lot of water, and it could well have flooded over the Appalachians and into what we now think of as the Ohio River Valley.
And if that same impact happened today, the East Coast would never be the same again. An asteroid attack has the power to instantly kill millions of people. The largest impacts can also cause global catastrophes, threatening the very existence of mankind. That's why the study of asteroids is one of science's highest priorities. 35 million years ago, an enormous asteroid slammed into America's east coast. The 55-mile-wide crater was hidden until recently, under Chesapeake Bay. Its effects were devastating. But what if that same impact happened today?
It would wipe out the East Coast essentially through a combination of tsunamis, blast waves, thermal effects, and it would also throw out huge amounts of ejecta that would spread to great distances, igniting additional forest fires.
It would be millions of people instantaneously killed or shortly after the impact. But it would have farther-reaching consequences, too, because of the overriding disruption throughout the entire region. Farming, communication, certainly our center of our government is on the East Coast.
But according to recently uncovered fossil records, the 1-mile-wide Chesapeake Bay asteroid didn't seem to have the same global effects as the massive extinctions triggered by the 6-mile asteroid that killed the dinosaurs.
The impact that created the Chesapeake Bay structure more than 30 million years ago was enormous, but it was still only a small fraction of the energy that was released during the impact in the Yucatan 65 million years ago. The impact was right on the threshold of providing truly global effects. Right on the threshold of what's required to make a mass extinction occur.
Because of that destructive power, it's crucial to know exactly what we're dealing with. And that means getting up close and personal, In 2001, the NASA mission named NEAR was supposed to just orbit the asteroid Eros.
But once it had got there and it had completed its mission objectives, the decision was made, let's try to land this thing, which is really, really fun. It's kind of old-fashioned exploration. Hey, go ahead and give it a try. So they did.
The images from the approach and landing gave scientists a much more detailed look at the surface of an asteroid than they'd ever had before, with some unexpected results.
One of the surprises looking at these small bodies is that they have geology. It had tectonic features and looks like it had landslides and erosion happening on its surface and impact craters all over it and boulders everywhere. And one imagines the scenario where a little asteroid comes along and hits a bigger asteroid, crashes into it, digs up a whole bunch of debris, and that slowly settles down, and these boulders just spread across the entire surface.
The NEAR spacecraft even transmitted information back to Earth for about 2 weeks while on the surface.
But it has lost its radio link with the Earth, and so now it's simply sitting there mute for millions of years.
The asteroid explorer Hayabusa of the Japan Aerospace Exploration Agency recently one-upped NEAR. It's the first spacecraft to ever land on an asteroid and then return to Earth. It arrived in June 2010 after a 4 billion-mile round trip.
As planned, most of the spacecraft burned up in the Earth's atmosphere, but the sample return capsule successfully landed in the outback of Australia.
Even today, it's still unclear if minute samples are present. The careful examination of the capsule is continuing.
It's a long process, but people are optimistic that we're going to get great data out of the first asteroid samples returned to Earth.
To a geochemist, a couple of micrograms of material is plenty to do some detailed chemistry and mineralogy and compositional work.
Even before Hayabusa returned, another asteroid mission was already underway.
3, 2, engine ignition, and liftoff.
After a 2007 launch, the NASA Dawn spacecraft is on its way to 2 of the largest asteroids in the asteroid belt between Mars and Jupiter. Dawn will arrive at 320-mile-wide Vesta in 2011, orbit for a year, then reach 600-mile-wide Ceres in 2015.
You couldn't find 2 asteroids more different from one another. Ceres is thought to be relatively wet, perhaps subsurface ices. And the other one, Vesta, is thought to be the opposite. It's completely lacking in hydrated minerals or water ice. It's been heated over its lifetime to such an extent that it's thought to be layered. A surface layer, a mantle, and a core, much like the Earth.
All of these missions are revealing that asteroids are made from a much wider assortment of materials than we first realized.
There's a huge variety in asteroids. Some of them are iron-rich or nickel-rich, very much like this iron dumbbell. Others are very similar to this earthbound rock. They're stony, they're rocky. Still others are a combination between the iron type and the stony type. We've also got exotic things like rubble piles, which are like having this handful of gravel, but if it all were gravitationally bound in a big asteroid kind of a form. We also have X-comets. And X-comets have gotten rid of all their ices, and we're left with this fine-grained material held in a very porous type fluff ball.
But asteroids are surprising us in other ways besides their composition.
The Galileo mission on its way to Jupiter went past an asteroid called Ida and discovered that it had a little tiny moon called Dactyl. This was a big surprise, and now we see that that's not so rare an incident. Asteroids do come with their own moons, sometimes several moons.
We're also learning that a lot of asteroids are traveling in pairs, as binaries, or even with 3 of them. And that's a very new set of observations and new thing to understand.
Knowing how asteroids are grouped and what they're made of is more than a matter of scientific interest. Imagine in the future that an enormous, deadly asteroid is speeding towards Earth. It needs to be deflected if mankind is going to survive. But if we don't know exactly what the asteroid is made of, then the effort to save the planet could go horribly wrong. An asteroid impact can unleash more destruction than just about any other kind of natural disaster. But it's also one of the few types of nature's fury that we may be able to prevent. Imagine in the future that a huge asteroid is racing towards Earth at 70,000 miles per hour. International space agencies have banded together and launched a rocket in an effort to save mankind.
The trick is to understand the enemy. Is it made of solid iron? Is it made of shattered rock? Is it made of a rubble pile, an excometary fluff ball? Because if you hit a slab of solid iron with a spacecraft, it's going to react far differently than an object that is a fluff ball.
The asteroid turns out to be a rubble pile. It's soft enough to mostly absorb the impact of the rocket and to stay on course to collide with Earth. It's also large enough that it doesn't burn up in the atmosphere. It hits and forever changes life on our planet. This is the price we could pay if we don't learn as much as possible about the variety of asteroids in our solar system. But at least with large asteroids, we should have years or decades of warning about their approach. With comets, even enormous ones, the warning time will be measured in months. Why? That's what Clayton L. in Atlanta, Georgia, wanted to ask the universe. So he emailed us. Why would there be so much less warning time before an Earth impact for a comet compared to an asteroid?
Good question, Clayton. We'd love to know when something might hit us. It turns out that asteroids are so nearby that we can track their orbits precisely. That means we can make accurate predictions of where they will be, tens or even hundreds of years in advance. That means we might be able to deflect them before they hit the Earth. Now, a comet comes in from the outer depths of the solar system and doesn't become bright enough to see until it's maybe 6 months or a year away from hitting us. So we have very little warning. Fortunately, most of the things that potentially could hit the Earth are asteroids, not comets. And we can track the asteroids pretty accurately.
The fact that asteroids have a much greater chance of destroying life on Earth sometime in the future is one of the main reasons why studying them with unmanned missions is so important. But in April 2010, U.S. President Barack Obama announced an even bigger challenge.
By 2025, we expect new spacecraft designed for long journeys to allow us to begin the first ever crewed missions beyond the moon into deep space. So we'll start by sending astronauts to an asteroid for the first time in history.
In my experience as a college teacher, the younger generations, they want to go beyond. Yeah, my grandparents went to the moon. You know, let's go beyond. And so that was an inspiring part of the president's message, that we need to get NASA back into the business of deep space.
A manned mission to an asteroid will be very different from moon missions of the past. In some ways, it will be easier, and in other ways, much harder. Whichever asteroid the astronauts visit will likely be a lot farther from Earth than the moon. So the journey will probably last for months instead of the 8 days it takes to get to the moon. But the round trip will actually use less fuel than a lunar landing mission.
When you go to the moon, you're dealing with a body with significant gravity of its own. You're having to use more fuel to safely slow yourself down and descend all the way to the surface. When you head to an asteroid with very low gravity, even though you're going farther to get there, you aren't having to expend nearly as much fuel for things like getting to the surface. It also takes less propulsion ability when you leave the asteroid to head back to Earth.
But landing on an asteroid surface will be much more challenging than setting down on the moon.
It's more like docking than it is landing. But you do have some gravity, so you have to deal with having a little bit of gravity. But you have to deal with actually anchoring yourself, holding on. You don't have to hold on when you're in the 1/6 Earth gravity of the moon.
Exploring a small rotating asteroid will also be much harder for astronauts than hopping around on the moon. It'll be more similar to a spacewalk.
Your sense of up and down is sort of screwed up. And you have to be very careful when you walk around on an asteroid because the gravity of the asteroid is so weak. A good jump can send you into an orbit around the asteroid or even send you out at escape velocity and escape from the asteroid completely. So you have to make sure that you're tethered down when you're exploring.
But since rovers have already proved to be so successful at exploring other worlds, is there a strong reason to send astronauts to an asteroid?
Astronauts, explorers, the public interested in space yearn to see what it's like in person through real human eyes. And that day is coming.
Robots can do a lot and have done a lot in space exploration, but there is no better geologist than a human being. To be a geologist exploring an asteroid and being able to recognize the history of a particular region, looking at familiar types of geological formations, you know just what you want to do. You want to go sample that rock, you don't want to go sample that rock.
Asteroids are also important because of the resources they might contain. The year is 2050, and a crew of astronauts has just landed their spacecraft on an asteroid. They're not here to explore. This is merely a pit stop. But what types of precious resources could this small rocky world possibly contain? An asteroid attack can wipe out entire species, including humans. But instead of accepting that fate, scientists are trying to learn enough about them to prevent disaster. And asteroids that aren't headed towards Earth may even turn out to be helpful.
One of the reasons to visit asteroids and to study them is that they may have some resources that could be useful to future human explorers. And among the most important of those would be ice, water. People are going to need ice to live and drink and use in a practical sense.
The year is 2050, and a crew on its way to Mars has just stopped at an asteroid for water and other supplies. The oxygen in the water can be separated to refill the crew's breathing tanks. But there's even more that this rocky supply station has to offer.
It's conceivable that with advanced technology, we could go to those asteroids, break down the water, and use the hydrogen and oxygen as fuel to take spacecraft even farther.
And there may even be priceless materials to bring back to Earth. Elements so rare and critical to high-tech success that they could be the cause of future wars.
Some asteroids have platinum and titanium and rare earth elements that are important in many aspects of electronics, which are called rare earth elements for a reason, because they're rare on the Earth. They might not be so rare in certain kinds of asteroids.
But the most important reason to investigate asteroids remains their ability to instantly kill millions of people or wipe out the human race altogether. To counter this threat, NASA launched the WISE mission in December 2009. The Wide Field Infrared Survey Explorer has already found 25,000 asteroids and more than a dozen comets that were too dark to find using visible light.
It's actually looking all around our solar system, hopefully to look at 99% of the sky and try and map more of these near-Earth objects, these asteroids that we haven't found in the past. And hopefully that'll help us in understanding if there are any that are in near-term collision courses with the Earth.
And even though it doesn't usually make front-page news, there are already plenty of asteroids that pass close to Earth. In April 2010, a 70-foot wide asteroid passed within 220,000 miles of Earth, which is closer than the distance from the Earth to the Moon. And a few months before that, a 23-foot wide asteroid came much closer.
In the winter of 2009, in November, there was an asteroid that passed so close to the Earth, it was only 8,000 to 9,000 miles away at its closest approach. And we didn't know about that until it got fairly close.
That's about the same distance as flying from Los Angeles to Mumbai, India. And back in 1972, a tourist's camera near the Grand Tetons in Wyoming captured a much closer pass by a similar-sized object.
The 1972 event was about as close as you can get to a collision without actually colliding. On its way in, it was going to collide with the Earth, but it skipped off of the atmosphere due to the pressure of the air, like a pebble being skipped off of the surface of a lake. That was a really close call.
Then, in October 2008, a small and seemingly uneventful impact occurred in a remote part of the African country of Sudan. But it actually represented a giant step forward in the science of predicting asteroid impacts.
A small asteroid was discovered, and it was predicted to land in Sudan the next day, and it did. Now, this is the first case we have of an object that was discovered and then predicted to land at a particular time and place. And in fact, fragments of this object were later found over the desert.
But that was only a small impact with a single day's notice. Today, the jury is still out on whether we'll be able to identify and deflect something that could inflict catastrophic damage on Earth. Scientists believe there are still millions of unidentified asteroids out there capable of destroying a city. Or worse. Will we be able to figure out which ones will cross our path? And will we be able to prevent them from slamming into Earth? The stakes couldn't possibly be any higher. Each new discovery in the world of asteroids isn't just a scientific advance, but an opportunity to increase the survival chances of mankind.